This is Math 432, Applied Combinatorics, and I am Professor Asaph. Today, we're going to start with a card trick. This is a deck of cards. You can see that they're in some kind of jumbled up order. I don't know what the order is. Here's what I'm going to do. I'm going to cut the deck, and my assistant, say hello, please.
Hello.
My assistant is going to tell me when to stop cutting the deck. Assistant, can you please tell me?
Stop.
Okay. I'm now going to lay down 5 cards face down that I cannot see. Okay, and I'll set the deck to the side. Assistant, I'm going to ask you to peek without showing me at each of these cards. If the card is red, put a red token on it.
And if it's black, put a black one.
Yeah, okay, you know how to do it. Go for it, assistant.
All right, this one's hard to get out. Got it. Great.
All done?
Yeah.
Fantastic. So I can see my assistant has now labeled them with red and black. So I know that these ones are red and these ones are black. So now, without having known the order of the deck and without knowing what these cards are because I wasn't looking. Assistant, was I looking?
No.
Okay.
Her back was turned.
That's right. Okay. So now I'm going to tell you what all the cards are. And I'll start with this one. It's a red card. So I know that its suit is either going to be a heart or a diamond. But I'll tell you that I happen to know the suit is going to be a diamond. Definitely a diamond. And now, how big is the card? What's the value of the card? I believe this card is actually a pretty small card. It's the 4 of diamonds. Aha. Now I'm going to think about this card. It's a black card, of course. So, being a black card, can I figure out what it is? Well, she told me that it was black, so that's not really that exciting, is it? Well, I think it's going to be a spade. Yeah, it's definitely a spade. It feels like a spade to me. And now, what am I thinking in terms of the value of the card? The value of the card. I think it's going to be very, very small value. In fact, I think it's probably going to be the ace. I think that's what it is. The ace of spades. Indeed, indeed. Okay, the next card. So I have to figure out what the next card is. So I'm going to do the same sort of game. It's red. Okay. It's actually going to be a diamond. And it's actually a very small value, but a little bigger. It's the 2 of diamonds. Okay. Next card. What's the next card? Maybe I'll speed it up a little if I can. This one is black. It's actually going to be a club. It's not a spade. It's a club. It's a smallish value again. It's a 4 of clubs. And the last card, also black. This time it's a spade. A slightly larger value spade. It's the 8 of spades. Now, how did I figure that out? In fact, I could actually keep going. I could tell you this card here. This card's the 8 of diamonds. And I can tell you this card. This card is the 8 of clubs. And I can tell you this card is the ace of clubs. And I could keep going through the whole deck like this. How? When the only information I was given were the colors of these 5 cards. This brings us to the beautiful topic of, let me try to keep these in order, the beautiful topic of De Bruyne sequences. What is a De Bruyne sequence? A De Bruyne sequence is a cyclic sequence of length 2 to the n, such that every subsequence of length n is unique. So let's do an example. Let's do an example where we take n equals 3. I claim the following is a De Bruyne sequence of order 3. 0, 0, 0, 1, 0, 1, 1, 1. Now, why do I claim this is a De Bruyne sequence of order 3? Well, let's look at it. So first of all, it needs to have 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. Yes. And it's binary. It's a binary sequence. I should have said that. So it gets zeros and ones. It gets bits of information. And now every subsequence of length n is unique. What are the subsequences of length n? Well, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, and 1, 1, 1. So what I need to do is for each of these sequences, I need to make sure that it shows up exactly once. Well, here's 0, 0, 0. Okay, what about 0, 0, 1? Well, here is 0, 0, 1. What about 0, 1, 0? Well, here is 0, 1, 0. What about 0, 1, 1? It's right here, 0, 1, 1. So we've got that one. What about 1, 0, 0? What about it? Remember, this is a cyclic sequence, so I need to wrap back around. And here is 1, 0, 0. So you can go through the rest like this and check that I do, in fact, have a De Bruyne sequence. And now we could have smaller De Bruyne sequences, of course. So if I wanted to do a De Bruyne sequence of order 2, there's not very many of them. In fact, there's only one. And you can check that there's only one of order 1 as well, but there are actually 2 of order 3, and then we get more and more. And we'll see how to count those in a minute. But first of all, what does this have to do with the card trick? Well, a bit of information is enough to tell me one of 2 things, right? Red or black. But what happened? What did the assistant give us? How many bits of information? So remember, with the 5 cards that we had, these were the 5 cards, she gave me 1 bit of information for every card, and there were 5 cards. So she gave me 2 to the 5 equals 32. 5 bits of information gives me 32 data points. Now, how does that help? Well, it turns out that this is not a full deck of cards. This is actually a deck of cards where I've taken out everything above 9. So we're going to use 2 bits. Oh, I'll pick those up in a sec. 2 bits to give me the suit. So I decided that the suits would be encoded with the first 2 bits of information. So 0, 0 is what I decided would be a club. And 0, 1 is what I decided would be a spade. I like doing it this way because the 0 tells me black. Okay? 1, 0, and 1, 1 are my other 2 sequences I could have. This will be a diamond, and this one was a heart. Then I used 3 bits to encode the rank. And I did it in binary, letting this denote 8. This would be the ace, and then so on and so forth in binary. So if we're doing that and we look at our cards and we take them in the order they were in, the first card I had was the 4 of spades. So how would the 4 of spades be encoded in this system? The 4 of diamonds. A diamond is 1, 0, and then the 4, right, in binary is 1, 0, 0. That's how I would encode this card. Here's its suit, and here is the rank of 4, the 4 of diamonds. Now notice, when we had this sequence of cards, what was revealed to us was 0 or 1, 1 with these 3 zeros. That's exactly, red is 1, 0 is black. So this original sequence of the bits of information given by the assistant exactly told me what the first card was. That's fantastic. So I used information to encode it, and I have 32 cards in the deck, and I have enough information to know about the 32 cards. But how did I know the next card? So I knew the 4 of diamonds because that's how I've encoded it, and there's a bit of magic in there still. But how did I know about the diamond, or the ace of spades was next? Well, for that, it turns out that some De Bruyne sequences have recurrence relations. This is a order 5 De Bruyne sequence. There are 32 bits listed here in a particular order. Each bit of information encodes, each string of length 5 is unique and tells me what a card is. So for this particular example, if I took here, this length 5 sequence 1, 0, 1, 0, 0, that is exactly the 4 of spades that I had, or sorry, I keep calling it a spade, the 4 of diamonds that I had down here. That's what matches up here. So what's the next card? Well, if I think about what's the next string that I have. So if I'm in a De Bruyne sequence, this is unique. This is the only place this string of 5 bits occurs in this order. So now I know, based on this recurrence relationship, that this digit here, I know if I take this and this, the thing in position 0 and in position 4, and I add, 3, and I add them up in binary, I'm going to get the next number. That's this recurrence relationship that generates this sequence. So what does that tell me? That tells me that the next card, I know, so I know there's a 1, so I know what the next card is. It's 0, 1. Remember, our encoding scheme said that 0, 1 would be a spade. 0, 0, 1 in binary, that's the number 1, which means the ace of spades, which indeed is what comes next. And then I can keep going like this. I say, okay, well, I knew this was a 1, and now that's why I got a little slower. I had to keep track of this in my head. But if you practice it, and I recommend it because it's a really fun trick to do, you can keep going. So now I'm going to take this guy and add it to this guy. 0 plus 0 gives me a 0, which is the next term in my sequence, which of course we can see because remember, the sequence is cyclic. It wraps back around. And now I look at this string of 5 things and I ask myself, what card is that? 1, 0, 1 meant red, 1, 0 meant diamond. And we have, 1, 0, and now we have 0, 1, 0. In binary, that's no 1s, a 2, no 4. So it's just the number 2. So I should get the 2 of diamonds, which indeed is what I get next. And then I just keep going. I take whatever the next one is. I believe I can take this color now. So I take this guy and I add it to this one. And I do it in binary. So 1 plus 1 is actually 0, mod 2. So I get another 0, which of course we can see, yes, I got the 0. But now I've got this string, which is right here. And I can figure out that card. Double 0 means I'm working with a club again. 1, that's a 4. No 2s, no 1, so this is just the number 4. So it's the 4 of clubs. So this is a really awesome trick, and I'll go over this one again in class. This is a really amazing trick that has to do with encoding information and with this idea of using a Bruyne sequence. But it still begs the question, how do we know Bruyne sequences even exist? It's sort of an amazing property that they have. And for that, brings us to the topic of this series, which is directed graphs.